My name is Alexander Knopp, and this is Introduction to Mathematical Reasoning. In the previous video, we discussed sets of real, sets of integers, and infinitely many other sets. In this video, we are going to discuss how to assign elements of one set to elements of another set, aka functions. In school, we studied functions, and when we say the word function, we imagine something like this. So we have a graph of the function, it's something like this. So this picture said that to every point here, we assign a point here. In other words, to every positive real number, we assign a positive real number. And in mathematics in general, instead of reals, we say we can assign an element of a set y to every element of a set x. And now it doesn't matter if it's the set of reals or some other set. So we say that a function f is from x to y if it assigns a unique element of y to every element of x. And we write this element as f of x. The definition wasn't quite formal. Let's try to formalize it using the notion of quantifiers. We use quantifiers in everyday speech quite often. For example, we may say, there is a red sock in my drawer. Or you can say, OK, all the socks in my drawer are pink. And in mathematics, we can use similar constructions. The first example of a quantifier is existential quantifier, which is a synonym of the phrase there is. For example, if you have a predicate P of A about the elements of the set B, then this formula states that there is an element of B such that it satisfies the constraint P. Or you can write it alternatively and say that the set of all elements of B satisfying the constraint P is not empty. Let's consider an example. So let's imagine that we have a real x. Then let's consider the statement. There is a real y such that y squared is equal to x. In other words, the statement says that there is a square root of x. We can rewrite it using the existential quantifier in the following form. There is y from real numbers such that y squared is equal to x. The second example of a quantifier is a universal quantifier, which is a synonym of the word all. For example, if we have a constraint P, then this formula says that every element of B satisfies the constraint P. You can rewrite it in the following form. The set of all elements of B satisfying the constraint P is equal to the set B. Let's consider an example of a universal quantifier. We may consider the statement like this. For every real number x, there is a real number y such that x is equal to y squared. This statement says that every real number has a square root. So you can rewrite this formula in a very succinct way. So every x from reals, there is y from reals such that x is equal to y squared. The second component of the definition of a function is Cartesian product. So if you have two sets, x and y, then their Cartesian product is a set of all possible pairs of elements of x and y. Note that the pairs are ordered. In other words, if you exchange two elements, the pair is different unless both elements are equal to each other. Using these components, we may give an alternative definition of the notion of functions. For example, a function f from x to y can be described by a set D, which is a subset of the Cartesian product of x and y, such that the following constraints are true. The first constraint states that to every element of x, we assign a unique element of y. So the first constraint says that we assign something. So for every a from x, there is b from y, such that ab belongs to D. And we need to say that this b is unique. So for every a from x and b1 and b2 from y, if both of them are assigned to a, then they should be equal to each other. So if a and b1 belongs to D and a and b2 belongs to D, then b1 is equal to b2. We can also write this set, if you know the values of f, like this. So D is equal to the set of A, comma fa, where A belongs to x. We call such a set a graph of a function. And it's obvious that if you know the graph, we can define a function, and vice versa. Using the quantifiers, we may define some properties and operations on the functions. And the first object is image. So if you have a function f from x to y, then image of f is a set of all elements of y that are assigned to some elements of x. In other words, b belongs to the image if there is an element of x such that f of a, this element, is equal to b. The second object we may define is the notion of restrictions. So let f be a function from x to y, and g be a function from a to y, and a be a subset of x. So we say that g is a restriction of f on a. In other words, f restricted to a is equal to g, if and only if for every element of a, f of a is equal to g of a. Finally, the third definition is the definition of a composition. So let's imagine that you have a function f from x to y, and you have a function g from y to z. Then the function h from x to z, such that the value of this element is equal to the same as if you go via these two functions, is the composition of them. So in other words, let f be a function from x to y and g be a function from y to z, then h is equal to a composition of g composed with f if and only if for every element a of x, h of a is equal to g of f of a. In this video, we defined functions, we defined quantifiers. Using them, we gave another definition of a function, and we defined several properties of the functions. If you have any questions, ask them in the comments. See you later.